For this problem, we're going to use proof by contradiction to prove a statement of the form not P. And the way that works is, well, to prove that P is not true, we assume it is true and we derive a contradiction from that. Okay. So here's the problem. You use the method of proof by contradiction to prove the following theorem. Suppose that A intersects C is a subset of B and A is an element of C. Then A is not an element of A minus B. So let's try and draw a picture and get a feel for why this might be true. So we have two sets A and C, which are, well, and we're interested in the intersection. So let me draw them like this. Of course, they might not overlap, right? The intersection might be the empty set, but this is probably the more interesting case when they do overlap. Okay, and we're supposing that their intersection, this overlap here, is a subset of B. So B is going to be something that contains that intersection. And then the conclusion is that A is not in A minus B. Okay. Now A minus B is the part of A that's not in B. So it would be, I feel like I'm in kindergarten trying to color inside the lines here. It'd be this part, right? And we've assumed, I forgot to mention, we're assuming that A is in C. So A is somewhere over here. And it's pretty clear from the picture that it can't be over here. All right. So let's try and work through the logic of that. Our givens are here and our goal is there. And for proof by contradiction, I'm going to think of this as not P, right? In which case P would be that A is contained in A minus B. Okay. So let's assume that A is in A minus B and try and derive a contradiction from that. And we can bring down our other givens. And okay, we need to combine these givens somehow. So perhaps we should first write out the definition of what it means for A to be an element of a difference of two sets. And it just means that A is in the first set, capital A, and A is not in the second set, capital B. Okay, so bring everything else down again. And now looking at what we have here, if A is in C and A, then it's going to be in A intersect C by definition of intersection, right? So we have that, and bring everything else down. All right, and now if A is in there, then we know by definition of a subset, that means that A would also have to be in capital B. Okay? So let me not bother to write out the definition of a subset. Just put those two together and get that A is in B. Bring down the rest of the stuff, and then there's our contradiction. Right? There's no way that A can be in B and not in B at the same time. So that finishes it. Let's try and write it up. So the way we introduce a proof by contradiction is to say what we are sort of supposing or assuming, right? In this case, that A is in A minus B. So suppose for contradiction that A is in A minus B. All right, well, the first thing we did was to write out the definition of that. So then A is in A and A is not in B. And so by the definition of set difference or set subtraction, I'd probably do set differences. Good way to say it. And once we had that, we combined that A is in A and A is in C to see that A is in A intersect B. So because A is in A and A is in C, it follows that A is in A intersect C. It's just the definition of intersection of two sets. And then once we had that, we used a definition of subset to get that. Well, if you write that out, then you need to use modus ponens as well to conclude that A is in B. Okay, so because A is in A intersect C and A intersect C is a subset of B. It follows that A is also in B by definition of subset together with modus ponens. And lo and behold, A and B, that I'll say this contradicts the fact that A is not in B, okay, which we had up here, right, from our assumption. So that's it. And just to sort of close off our proof by contradiction, we should say what we've proven. So therefore, A is not in A minus B. Okay, right? We assumed that it was. We got a contradiction. Therefore, it's not. And as usual, this last statement is sort of optional, so I'll put it in brackets. And we're done.